Machine learning applied to games without human input. The way that this works generally is you have a neural network, and it works in conjunction with MCTS, which is short for Monte Carlo search tree, to play random games and use the results of those random games, or games played at random, in order to train the neural nets. Okay, and the first part of this that you need to know and have under your belt is the MCTS. What is it? And I can go over it here, but I could never do a better job than this guy here. Okay, so go ahead and search for his video, John Levine, a Monte Carlo search tree. He goes over the general overview of what it is. He goes over the nuts and bolts of the function that is driving the search of the nodes, and then on top of that he goes over the algorithm running through the paces as nodes are being searched. If you take a look here, as nodes are being searched, what values are contained in each node and how they're updated. He runs through the algorithm a couple iterations, so can't have a clearer explanation than that. So thank you, John. And coming back over to here, generally speaking, what is the Monte Carlo search tree? Well, we have a state that we are currently in. We'll call it state 0. And from that state, we have possible moves, right? And it'll lead us to a second separate state. So state 1 all the way up to state 11. No, that's wrong. State 12. Because our 2x2 Rubik's Cube, which is what we're applying this methodology to, has 12 possible moves for each state, right? 12 possible ways to turn the faces. And I think that might be the number for a 3x3 Rubik's Cube, right? We're working with a 2x2, but regardless, let's pretend that there are 12 possible moves. So we're going from state 1 to state 12. And the MCT uses a function in order to determine which of the states to select to explore, right? And the equation is here. Okay, so whichever node maximizes this function here is the node that is chosen. And we don't really need to get into the nitty-gritty, but all we need to understand is that the equation, right, so the chosen node is equal to two components. There's the first component, and then there's the second component. The first component is the exploitation. And the second component is the exploration component. Okay, so this portion of the equation says if a node has been previously visited and has a strong value, meaning there has been quite a few wins found through that node, then it has a higher chance of being chosen as the next node to be chosen, to be explored. And that's good, right? Because the more times a certain pathway has found success, the more successful of a path it is. And you kind of want to keep going down that path and see if you can find more success going down that path. The second portion here is the exploration portion. And what that is it values nodes that haven't been chosen often. So if we have a let's say an S3 over here, and S3 has not been chosen, hasn't been explored, right? So its node values will be low, and this portion encourages S3 to be chosen. So then you get a balance of choosing nodes that have strong previous history of wins with nodes that haven't been explored. And what that does is it creates a intelligent way of running through the nodes here, because you don't want to just keep going down the same path, right? Because if you keep going down the same path, yeah, you might find that there is a win here, right? And then with those wins are, low numbers. Let's say they're under 10 moves to the wins, right? And let's say we went down this path many, many, many times, right? And we had various wins, and they're all less than 10. But what about over here in S3, right? And he gets to a win, right? He has a series of ways to get to the win, and his series of ways to get to the win are under 5, right? But he hasn't been chosen because S1 is continuing to be chosen, and he's explored, and so his strength is increasing because of the exploitation portion of the equation, right? That's why we want the exploration portion as well. The exploration portion is going to say, hey, let's not get stuck down one path. Let's go ahead and take a look at other paths and see what they have to offer, right? Okay, so that's the MCTS, and the way that the MCTS is going to work is that once it chooses a node via this equation that's outlined in the video by John Levine, let's say this is the node that is chosen, what it's going to do, let me get rid of the equation actually. What it's going to do is it's going to run random moves, random moves until it finally gets to a win state. All right. When it does that, it's going to come back up to the top, and every one of the nodes, and then the values for this node S1 are going to be updated, which is going to affect whether that node is going to be chosen for a second round, right, for a second rollout. So we're going to update the values in S1, run it through the equation again, pick the next node via the equation to search. And let's say we pick this node over here, and he runs down until he gets to a win, right? Random moves to a win. And then based on those random moves to the win, the values up in this S, let's call it S3, are updated. And then the equation is run again to choose another node. So that happens over and over and over again. And the details of that algorithm are explained in the video. Okay. So what I want to go over is that when S1 rolls out, that's what we call this. When S1 is chosen, let's say a state is chosen, and random moves are run on state 1 over and over and over again until it reaches a win state. Right. So what you're ending up with is you have a series of states of the Rubik's Cube or the game board or the state of the game. So let's say game state 1, right? It consists of a set of data representing the state of the game, right? And then we have game state 2, which has a series of data that represents the state of the game. In our application, it's going to be the 2x2 Rubik's Cube faces, right here and here. And then we're going to keep on continuing down as we do random moves until finally it gets to game state N, and game state N has a set of random moves. It has a record of the state of the cube, and it shows that it's a win, right? So all 6 faces of the Rubik's Cube have the same color in this final state, and it's a win. All right. So this is called a rollout, and roll out. And after this rollout has completed, then it comes back up, updates S1's variables that are stored there, and then it runs through the MCT algorithm again and does another rollout. Now, different applications of the neural net and MCT have different characteristics. What I read over in AlphaZero, when they went ahead and programmed AlphaZero, this is the system that they used, and they rolled out 1,600 times. Okay, so they did this process 1,600 times. So what they would have is 1,600 sets of game states, which eventually leads to a win. All right, so we have that. Now, that's the MCTS. I think now would be a good time to talk about the neural network. And so the neural network, what it is a set of 2 networks. It's the value network and it's the priority network. The value network is going to be fed a game state. So let's say network value is going to be fed. It's going to be fed a game state, and it's going to go through the network. I'm just going to put 3 of those crosses to signify a network there. It goes to the network and it outputs a probability from -1 to 1. Right? So a 1 is a win and a -1 is a loss. Okay. But the neural network is not going to output -1 or 1. It's going to output a fractional number close to -1. If it's strong loss, it's going to output a negative number that's close to +1 if it's a strong possibility of a win, and it's going to most likely give you a number in between -1 and 1, right? So like 0.25, possibly -0.33. And so those are telling you whether the probability is that state's going to lead you to a loss, or whether that state's going to lead you to a win. Okay, so that's what the value network does. Takes in a game state and tells you, is that state going to lead to a win or a loss? Now, and then we have the priority network. And what does the priority network take in? It takes in a game state into the network priority, and it outputs the best possible move. So we have move sub 0, or I guess we could say state 0, state 1, all the way to state 11, right? Because we're working under the framework of the Rubik's Cube, and let's assume that there's 12 possible moves per cube. So what does that mean? That means if given a game state, the best possible move would be represented by a set of 10 game states, right? Each of these would be one move from the original game state. This would be one move from the original game state, and so on, right? The different possible moves. So what the priority network does is it takes in the game state and it outputs probabilities on each of these states. The probability of state 1 being the right move, the probability of state 2 being the right move, all the way to the probability of state 11 being the right move, right? The 12th state, or the 12th possible move. So the priority network tells you what's the best move given a game state. The value network tells you whether that game state is going to lead to a win or a loss. Okay, and that's what the algorithm is using when you are trying to learn a game without human input through random analysis of random moves. Okay, so that's that. We have the value network, we have the priority network. Now the question that you should have, and the question that most people will have, is, okay, well, how does the MCTS work with the value network and the priority network, so that we can train the priority network in such a way that it will intelligently destroy the best Go players in the world, right? Because that's what this system does. What we're talking about here is a basic framework. If you dive into AlphaZero, you'll see that there's more to it. Right? There's little tweaks and adaptations and different methods that they implemented, but generally speaking, this is what's happening. Okay, so how does it work? The priority network is what we want. Who cares about the value network, right? Who cares? Like in the end result, what's happening is that we care what the priority network is telling us. We care about what the priority network is going to tell us what move to move to. And the value network is a supplementary network. It helps. Okay, it doesn't provide us any information about which move we should move on. It receives a game state, tells us whether it leads to a win or a loss. That tells us that tells the player, the computer player of Go, nothing about which move to move towards. The priority network does, because you give it a game state and it tells you which move you want to move to. Okay, so this is what we're training. This is the important part. This is supplementary, and I would think of this as being our heartbeat. Okay, our heart. This is I can't even make a comparison, but okay. So how does this work? All right. So when the MCT goes ahead and rolls out, right, it's given a state. This is the current state of the board, or current state of the game, or current state of the cube. Then it rolls out the MCTs, right? So it runs through MCT. Let's say that 1600 is the amount of rollouts that we're setting our MCT to run. So on the first iteration of the MCT, it's going to select, let's pretend it selects S1, so state 1. What is that going to do? Random, down to a win. Along the way, it's recording all of the states of the game that result from those random moves, right? And one thing you need to consider is that all those random moves lead to a win. They lead to a win. So because they lead to a win, what we can do is we can add a value on the end of each of these game states. And we're going to add a 1. What does the 1 signify? It means that these game states of the cube led to a win. Every single one of them, right? However many there are. If there's 260 of them, or whether there's 3,000 of them, or whether there's 10 of them, right? The rollout is random, so we don't know how many times it's going to go ahead and choose random moves. But every one of those moves is recorded, and a value of 1 is attached to them. So after one rollout has completed, what happens is it takes all of this information, all the game states, along with the fact that they led to a win, and it uses it to train the value network. The game state is fed into the value network. It trains the weights and biases through the network, and then the value that we give the network is a 1 on that game state, right? So then it uses that assumption that that game state was a good game state and the value should be 1 to train the weights and biases through backpropagation and all of that we covered in the past. So it does that for the first game state that was recorded. Does it for the next one, the next one, the next one, the next one, the next one. Does it for all of them. So for each step in the rollout, it uses all of those game states to train the value network. Okay. Then what happens? Well, then MCT goes ahead and selects another node to explore, finds it, rolls it out, randoms down to a win, saves all of those game states, and feeds those game states to the value network. So as the MCT is rolling out, it is training the value network on verified won games. Okay, and the MCT is exploring nodes that have a strong possibility of winning because they've showed wins in the past, right? Because we have two parts of the equation. We got the exploitation, right, shown wins in the past, so we should explore that. But it also has the other portion that rewards exploration, so it's also exploring, right? So it's an interesting algorithm here, and it's feeding our value network won games and training our value network on win states, or states that led to the win. All right, so that should be pretty clear. And now you might be thinking, okay, but what about the priority network? How is that guy trained? So the way now here comes a couple of different interpretations, right? So I spoke with Jeremy. He gave me one interpretation. I kind of thought about it myself, and I had a first initial interpretation. So I'm going to give you both of them and let you think about it. And as you're reading through the articles and the blogs and whatnot, you can decide which one is the valid one, because I don't think it's exactly clear, So what is my interpretation? My interpretation is that the MCTS is going to roll out 1,600 times, right? And at the end of those 1,600 rollouts, it's going to use the values stored in each of the possible move nodes to decide which move is the best move to move forward with. That's what MCTS does, right? It runs through all these rollouts, and at the end of running all those rollouts, or after running a certain number of rollouts, it determines, based on the values stored in the nodes or the possible moves, which of those possible moves has the highest percentage of being a win move or leading to a win. So let's assume that S1 has been declared after the 1,600 rollouts to be the win move, right? As the rollouts are happening, value network is being trained on every one of those win states, or states that led to a win. After the 16 are over, it's decided S1 is the win move, right? So what I'm thinking is that the MCTS gives that state S0 to the priority network as the game state, and it says that S1 is the win. Or in this case, it's our S0 is the win. This is our first state, okay? So it says that S0 is the win, and it uses that assumption to train the priority network. Okay, so what does that mean? That means after 16 rollouts on the MCTS, we train the priority network once with one game state. And then what happens? Then we go again, right? Another 1,600 rollouts after we make our next move. And then after those 1600 rollouts, then we have which node is the win, and we feed S sub 0, the new S sub 0, to the priority network using that new state that was chosen via MCTS as our win state, which we're going to use to train the network, right? Adjust the weights and balances so that it will choose S1, more often the next time. So that was my initial interpretation. Might be right, probably wrong. Okay, so after hearing Jeremy, I'm thinking Jeremy's right. And so what's Jeremy's setup or understanding? His understanding is that after each rollout, right, the game state that led to so this is like the game states of the rollout. So after that rollout has happened, a win has been determined. We put 1 on all of these game states. We feed the first game state into the value network, right? We train it, saying that was a state that led to a win. Train the network. And then what we do is we have a state in the priority network. So like, let's say state current, right? This is the current state of the, or I guess right here we called it S sub 0. So we call it S sub 0, the state 0. And I guess this one should be 1 then, and this guy should be 2. So S sub 0, right, has different possible moves. It has state 1 move, state 2 move, a move that leads to state 1, a move that results in state 2, and a move that results in state n. So what is going to happen is that we are going to feed S1 into the value network. We're going to feed S2 into the value network, S3, S4 into the value network, each time receiving a probability that state will lead to a win or a loss until we go through all of them, right? So SN or S12, whatever it is. So we feed all of these guys into the value network after it has been trained once. And you want to remember that these value networks are randomized when they first start out, right? All the weights and balances are randomized, and they're extremely unintelligent. We trained the value network with 1 game state, right? Which means all the weights and balances of this network here have been adjusted slightly. Not all of them, but a set of them have been adjusted slightly, making it slightly more intelligent, but still incredibly random. Right, would not beat even the the monkey who's randomly smashing keys on the keyboard, most likely. So, and then we take that dumb network, let's call it an unintelligent network, and we use it to determine which of these states, S1, S2 to S12 or SN, have the highest probability of leading to a win. And again, when we first start this algorithm out, it's going to be extremely unintelligent. Okay, but that's how we're gonna start out. That's how we're gonna start. And then what is it gonna do? Then the priority network is gonna take the return value of the value network on each of these possible states, each of these possible moves, and say, oh, okay, well, hold on, let me get back over here. Okay, well, S2 gave the value network gave S2 the highest probability of being a win. Let's say it was 0.4, like 5.1, right? Let's say everyone else, all the other states were less than 0.5. So S2, according to the value network, has the highest probability of leading to a win. So then that's what the priority network trains itself using. It uses state 0, which is right here, our current state, and it uses S2 because the value network has chosen it to have the highest probability of leading to a win. And then it uses that information to train the network once, right? Through forward propagation and then back propagation. Then what happens? Then we give it the next state that led to a win, and we do the same thing. Then we give it the next state that led to a win. We train the value network, train the priority network, and then we do it again and again and again until we get through all of the states that led to a rollout. So Jeremy's suggestion, which most likely is correct, is that for 1,600 rollouts, right, that means that 1,600 times that the value network is going to receive a set of states and be trained on each of those states. That also means that for each of those 1,600 times, the priority network is going to use the current state of the value network to determine which of the final states is going to be the win state, and use that win state that the value network has decided to train the priority network, saying that is the winner. And that's what we want to move towards. Now, again, when we first start out, this is all going to be random. It's going to be all random, and the network is going to be very unintelligent. But the more and more it runs through the MCT and through the value network and through the priority network, and the value and the priority network have opportunities to adjust their weights and balances, the more and more it will creep towards intelligence. And eventually, the priority network will have its weights and balances tuned in such a way that it will be able to choose the most intelligent next move based on the hard data given by the MCTS's rollouts, right? The definite game states that led to a win, right? The very many that led to a win, and it will be able to defeat a human player, right? That's the goal. And there's different ways to analyze that at the end, but I don't think we're there yet. The first thing that we want to do is understand how this all works, and I think I gave a pretty clear explanation. And once we understand how it works, then we would want to code it. And so my feeling is that TensorFlow is not going to be helpful here, because I don't think TensorFlow allows the amount of customization that we would need in order to get this going, right? I think maybe a Python implementation would be better. Possibly, I don't know. I have to go ahead and take a look at it, but or we all have to take a look at it. But yeah, first it's understand what's going on. Take a look at what others have done in the past, and then let's go ahead and try to re-implement in our 2x2 Rubik's Cube case and see if we can get a neural network to intelligently solve this guy. And I think that's going to be huge if we're able to do that, because that is a simplified version of the more sophisticated implementations that have solved, I don't want to say solved, but have beat the highest ranked Dota players, that have beat the highest ranked Go players, right? So this is the basic framework that they're using. So pretty powerful stuff, and I think we can end this video here.